So I hope you will excuse me if I couldn't cite everybody who worked in holomorphic dynamics in dimension 1. And for example, we didn't even touch what can happen if instead of taking a polynomial or a rational map, we take a transcendental entire function. Okay? So before going to higher dimension, there are two things that I have to put at the blackboard. First of all, I have to remind you, well, I reminded myself of the good definition for a Chebyshev polynomial because this was asked. So a Chebyshev, I never know how to write it. I think it's a Y. Polynomial is a polynomial, well, it's actually you have a whole sequence of those. And Tn is a polynomial, so it has complex, actually not complex, but whatever, coefficients. And it satisfies in such that, well, Tn of cosinus of theta is equal to cosinus of m theta. So you can amuse yourself as an exercise. Compute, well, T1, T2, T3. Compute the first ones. Actually, you can find, if you go online, you will find some better way to compute them. Actually, you can compute them recursively. So you can compute the, how to say it, the, well, Tn by knowing the previous one. And actually, you can compute the multiplier at fixed points, different from infinity. So remember, as we said, infinity for a polynomial is always a fixed point, which is super attracting. So if you take the finite fixed points for these two, I mean for these three, for T1, T2, T3. So if you do that, you will notice that you only have integer multipliers. And this goes back to, well, you could also, I mean, let me just mention it because it's interesting that you know it. There is also some branch of dynamics, complex dynamics, who is more interested in studying the arithmetic properties of dynamical systems. So for example, well, this is not a very good question, but people that work on it, how many rational points you could have, how many rational periodic points you could have for a algebraic dynamical system. So you give yourself a polynomial, and then you try to count the rational periodic points. So I don't think it's a good question because, as we saw, we can conjugate things. And so rational points are not going to stay invariant under conjugation. What it is more interesting is to understand the properties of the multipliers, because the multipliers, they stay invariant. So we can ask, what happens if I have infinitely many multipliers for periodic points, which are integers? Can I characterize these maps? So these are questions that are more related to arithmetic dynamics. We will not enter this, but just for you to know that, you know, life is, well, mathematics is big, and you could try to answer these kind of questions as well. Okay, this one I'm not going to use it. And another thing that I forgot to mention is that you remember we have Fatou's classification of invariant Fatou components. This is not good. I think there was something better. Yeah. Okay, this should work better. For rational maps of degree at least 2, we have Sullivan non-wandering domain theorem. But this theorem works for irrational maps, so on the Riemann sphere, in the compact case. So a natural question is this going to be the same if I have a transcendental entire map? So Sullivan result goes back to 1985. But actually, I think I noted down that, yes, Baker in 1975, okay, had already, 76, had already, yes, had already proved that there exists F from C to itself, transcendental, entire. So you can have an entire map, an entire function which is not a polynomial, think like exponential, with a wandering domain. And actually, later, well, Baker's construction was not a construction. So it was not giving you, it was giving you the existence of such a map without giving you the map. But you can have examples like maps going back to Hermann in 1984, Sullivan himself, again 1985. And just to give you, for example, the function f of z equals to z minus exponential of z plus 2 pi I. And, well, let's call it f1 and f2 of z equals to z plus 2 pi plus, minus sinus z have wandering domains. Okay, so for these maps, if I'm not mistaken, the wandering domain for this map is something like, so you have the real axis, and you have something like this, which you find back in the same way translated. So it's translated, so this is this is a Fatou component, and when you iterate, it goes to this one, which is different, and then to this one, and it translated, but 2 pi all along, okay? And so, well, it's never getting back. So, of course, it's never getting back because we are on the complex plane. But if we close the complex plane with a point, then this is no more a holomorphic map, so we cannot consider that. And, well, it goes back to itself. So, essentially, if you want to say it in one sentence, in dimension 1, the existence or non-existence of wandering domain, it's related to the compactness of your space. So if you're in the compact setting, you cannot have wandering domains. If you are in the non-compact setting, you can. All right? All right, so this is all I wanted to say in dimension 1, but of course, you could ask many, many questions. And so if you want to know more about one-dimensional holomorphic dynamics, I suggest you look at, so there are several books. So the classical book is Milnor's book. I never remember the title correctly, but it's like Dynamics in Complex Dimension 1 or Complex Dynamics in one dimension, something like that. And you also have Burden's book, Iteration of Rational Maps. And there is also Carlson Gamling, Complex Dynamics, is mostly in dimension 1. And all of those, so if you go to my webpage and to research papers, there is like a CIME lecture notes. CIME. Actually, you find it also on arXiv. You find it on my webpage, but you also find it on arXiv. and I wrote them with Xavier Buff. Okay, so you find in there, I put them online in February. So you can go there and you will find a huge bibliography. And of course, it's almost sure that I forgot something, but if you take that bibliography and then the reference in the reference and so on and so forth. Huh?
It's not one thing. Right.
Yeah.
No.
Yeah, no. It's not one drink. So you will eventually converge to having all the references that you need for this theory. So now we go finally to higher dimension, and you will see we will go to higher dimension and we will go back to dimension 1, because at the end I changed a little my mind and I decided that so what we are going to do in the next, today, tomorrow, and Friday, we are going to try and prove, have an idea of the result that we proved, together with a bunch of people, I will mention it later, that Sullivan's result is not true in higher dimension. Okay? And this proof uses techniques from dimension 1. And so since now we know some techniques from dimension 1, we have kind of the tools to get there. Okay? So since I was not at the exercise class yesterday, do you have any questions on what we've seen so far? It's okay if you don't. All right, so now let's go to higher dimension. So higher dimension with us will be dimension 2. So from now on, so let's go to dimension 2. And let's list for 1 second what we don't have. So we don't have Riemann's uniformization theory, okay? And we don't have also the restrictions of holomorphic automorphisms of C2. So, of course, we could go also to Cn, but C2 will be already enough. We will see what we need to see in C2. So, what do I mean by we don't have this, poorness of automorphisms of C2? Because you remember, in C, the only automorphisms that we had were affine maps. An affine map is no arm, and so we know, essentially, we know how to deal with them. We know how to deal with conjugacy, and we know how to construct models. But when we go to C2, we have a bunch of automorphisms. They could be polynomial, they could be non-polynomial, and how can we do? What is the right map that we have to look at? And what could happen? Of course, we have 2 dimensions now, and if you think about the real, if you think it as a real vector field, is a 4-dimensional real vector space with some structure, so it's a lot, all right? So where do we start from? Well, a first question is, so question 1 is, can we recover, what we know from dimension 1? Meaning, so in dimension 1, we had these invariant Fatou components who were like attracting basins, parabolic basins, elliptic, rotation domains, and so on and so forth. Can we have like combinations of direct products of all these guys? And question 2 is it really interesting to go to higher dimensions? So can we recover something new? What are the new phenomena arising in dimension 2? Because if we have to just, tire ourselves in proving exactly the same results that we knew in dimension 1, of course it will be more technical, of course it will be more complicated, but who cares? At the end of the day, these are the expected results. So if you referee as to refer your paper, they will say, yes, this was very technical, this was very interesting, but at the end of the day, they recovered exactly what they knew in dimension 1, so it's not interesting. So and what we are going to try to do is to, well, first, we can recover all that we know from dimension 1, that's nice. And second, well, there are new interesting phenomena, and so it makes sense to work in higher dimension. Even if we have so many few tools with respect to dimension 1, because we cannot say, oh, this is a simply connected proper subset of C2, then it's going to be biolomorphic to a ball. This is not true. This is really not true at all. All right? So, yes. So, for the sake of simplicity, what we're going to do, so we have so many holomorphic maps, so many maps that you could think of in here. So, we're going to take polynomial endomorphisms of C2. Okay? I'm not assuming that they are automorphisms. I just want to recover what I could say in dimension 1. So, if I had a polynomial function, so this was going to be entire, and I could say many things about the invariant Fatou components. So we're going to, so the setting is going to be, we'll take capital F from C2 to itself, a polynomial map. All right? And actually, I wanted to be of degree d at least 2. So what do I mean by this? Capital F of z and w, so I have two coordinates this time, is little s of zw, little g of zw, and f and g are polynomials in two variables. What also I mean, I also want to have them to, so I'm going to restrict myself, okay, of same degree. I mean, this is an hypothesis, okay? So this is something that I'm putting to try and have my life easier, okay? Yes?
Even non-polynomial, you say that automorphisms in C2 are much more complicated.
Yes.
Can you give an example of something which is not polynomial?
Well, actually, I can give it without writing it down. So you can take, so take something which is starting like the identity, okay? Z plus,
Oh, it's not an automorphism. Yeah, you are looking for an automorphism.
yes, and W plus Q of the W. So these are polynomials for the moment. This is not an automorphism, but what I'm going to say is that given a polynomial, so this is of degree d, at least 2, since it's invertible locally, there exists, so given such, so locally invertible, there exists by Anderson-Lampert theory, there exists an automorphism of C2 F tilde such that F tilde minus capital F is a big O of norm of ZW to the power L for every L bigger than D plus 1. So you give me a jet, so this goes back to jet interpolation, and you give me your favorite locally invertible germ, then they can extend it. Of course, if one wants something better, what you could also do is to have like a Henon map, which is transcendental. So a Henon map, okay, let me see if I don't do it this correctly. So this is Z minus P of, W minus P of Z, AZ. So this with A different from 0, this is the Greek for polynomial automorphisms in situ. So you build them with this and with the shift.
Yeah. I think
Okay.
that for C, there's more. We need
For-
two variables.
Exactly. You need two variables to do it. So polynomial, let me write it somewhere. Let me write it here. So this is a very deep result, which is only true in C2. In higher dimension, this is no more true, but in C2, polynomial automorphisms are finite composition of switches, meaning that you have h of zw, which is wz. So you switch the coordinates, and Henon maps. Meaning h of zw of the form w minus p of z, a of z, with a different from 0, because otherwise it's not an automorphism, and p a polynomial of some degree, of given degree. At least one.
And for CN,
For Cn, so this is, sorry, let me write it down because it's important that you know at least where it comes from. So this was proved, so this is a theorem of Friedland and Milnor. But this kind of, actually, somehow, well, they proved more. They also rediscovered some algebraic things that were already known to algebraists in dimension 2. In higher dimension, oh, this is nice, but I have to work harder to raise it. So maybe I will not use it back. Yeah, I used a different one. No, it's okay. I will manage. So I will not use it anymore because otherwise I'm not able to erase things. So in Cn, for n at least 3, this equality is no more true. So there are polynomial automorphisms of Cn which are not of this form. And this goes back to some algebra that I will not enter into, but it goes back to the fact that you had this, I think it's called amalgamated product of the group generated by this and the group generated by this one, and the description is more complicated. You have more space. Essentially, it's a matter of having a lot of space to do things, okay? So
one clarification. So in this setup, Henon maps are not considered, right?
yes, I'm not considering Henon maps, and I will explain to you why. Actually, I will change my setting in 1 second, and I will definitely not consider Henon maps.
I mean, quickly, Henon maps, I mean, both components don't have degree greater than, I mean, the second, that's also a reason. Is it true?
Huh? Sorry?
I mean, in Henon map, the second component has degree only 1.
Exactly, exactly. So why I want to, actually I didn't add the last thing that I want to have in here. Let me add it. So I want even more than this. I want them to, so I want them to do two things. They want them to vanish at 0. And this is just to make my life easier in coordinates. This is not a big deal. And the second thing that I want is, thank you. The second thing, I feel like a very spoiled person. I have people cleaning my whiteboard. This is really spoiling me. Thank you so much. And I also want them to have no common factor. And why do I want this? Because now, if I homogenize this, so therefore, if we homogenize F, we get a holomorphic endomorphism of C3 such that it is given by 3 homogeneous polynomial which have still have to work a little harder, but so which have the same degree d, and the only common zero is 0 itself. And so I can go to P3 of C. Okay? So you know what the problem is that I want to work with maps where maybe I can recover the properties that I had for a rational function. Okay? So that's the restriction that I want to put. I mean, it's a height restriction. I'm not saying that it's not, but you'll see that already with this kind of restriction, life is not as easy. And I don't want to work with Henon maps for the simple reason that Henon maps are too rigid. For example, an Henon map has constant Jacobian. And having constant Jacobian means that it does something to the area form. It means that if A is in modulus less than 1, it's going to contract the area form. And so for the eigenvalues at fixed points, I will have some properties because their product have to be of modulus less than 1. And if I have A of modulus 1, it's going to preserve the area. So I will never have any contracting thing like an attracting basing. Okay? So if I want to recover stuff in the best case possible, well, I have to leave the very, very restrictive setting of Henon maps. But I mean, it's very restrictive, but a lot has been done for Henon maps. It's really interesting. You can use pluripotential theory to work with them. I mean, a lot has been done, and a lot has been still doing in this Henon setting. For example, in India, there is a very nice group of people working in this kind of stuff, like Kaushal Verma and Sayani Bera and Ratnapal. I mean, they are proving nice results, also using currents and pluripotential theory. In here, we will not do that, but just for you to know, okay? Right, so, all right, so I didn't put, it's given by 3 homogeneous polynomials. I'm sorry, I'm going to erase here because it's really weird to not write from left to right. So, all right. And so, these 3 homogeneous polynomials will vanish together only at 0, which means that they will send C3 minus the origin to C3 minus the origin. And so I will recover a map, a holomorphic map, from P2 to P2. Okay? So, which I will not use much, but that's the thing that I have in mind. So I have P, Q, R, which are homogeneous polynomials from C3 to C3. And the intersection of their vanishing loci is simply given by the origin. Therefore, we get a holomorphic endomorphism of P2 of C. Meaning that we are trying to do rational dynamics in dimension 2. Okay? We're trying to recover what we knew. So the definition of the Julia set and the Fatou set is going to be the same. Again, if we are working with Henon maps, you could give a more precise definition of the Julia set. You could speak about currents and equilibrium measures. I will not enter into that. I will simply stick to, we take the definition we had in dimension 1, we just use the same definition, which makes sense. So the Fatou set is again the normality set of the family of iterates. And the Julia set is the complement, so it's C2 minus the Fatou set. And since I have a polynomial, what do I have is that, so if you think about it for 1 second, I'm going to draw C2. So, okay, I know that this is not C2, this is looking more like a R2, but if you imagine that this is a complex plane and this is a complex plane, this is C2, okay? So, in here, what's going to happen is that since I have polynomials, if the norm of ZW, if the norm of my point is very big, everything is going to go to infinity. Okay, so there will be some ball where everything goes to infinity. Somehow, I don't care how it goes to infinity. Okay? But what I'm interested in is what happens nearby here. So, okay, now I can restrict myself, and so if I'm not touching infinity, I can think of, I'm really working in C2. Okay, so I made myself work in a setting where I can work, I can, if I get a result, I can use it as a result on P2 of C, but in reality, what I'm going to do, I'm working in C2, and then I'll see what happens. Because I don't have to take care of what happens in infinity. Infinity is taken care of the fact that I have a polynomial. Okay? Right. So now, I erase my question, but how can we, so do you see an easy way? I'll give you the answer right away. So is there an easy way to recover these products of Fatou components? So I mean, I would like to have a map, a polynomial map of C2, like over there, which has a Fatou component, which is the product of a disk, like an attracting basin, and a parabolic basin. Can I do that? Of course I can. And I can also have the product of a Hermanning. No, sorry, a Hermanning I cannot do it because I have a polynomial. But I can have a Siegel disk with an attracting basin. How do I do it? In the easiest way possible. So there is a way to go to higher dimension without actually going there. You can ask, can I recover this product of things? Well, I already gave you the answer. Yes, by taking direct products. So if you consider, so considering a direct product, meaning f of zw, which is indeed f of z g of w. So, well, this is a map from C2 to itself, but you can see it more like a C times C to C times C. So we can recover, recover, well, all possible, and this is polynomial, of course, in our setting. We can recover all possible products of Fatou components, of one-dimensional Fatou components. All right? So you can have an attracting disk times an annulus, an Hermann, still thinking about it because I have something else in mind. A Siegel disk, you cannot recover the annuli. Okay, you cannot have Hermann rings because you cannot have them toward these two guys. Okay? You can have a parabolic basin times a parabolic basin. Everything that you knew. What cannot you have? You cannot have wandering domains. So, but we cannot get a wandering domain nor anything new. So what do I mean by this? We would like to see, okay, what happens if I have a point where the differential is an elliptic rotation. I have like e to the 2 eigenvalues, e to the 2 pi I theta z, e to the 2 pi I theta 2 w, and these are irrational. What happens there? Can I do something? Or what happens if I have the two eigenvalues which are 1? Do I always have a product of such type? Can I have something different? I don't know. I mean, so I don't know means that with this direct products, you cannot. So you cannot have anything different, which means that considering direct products, it's just a mere exercise of applying what you know from dimension 1 to dimension 2 without even introducing new things. So now, new techniques. So now, well, if you want something less stupid, well, you can, but you still want to build on dimension 1 because that's the thing. You would like to use what you know from dimension 1, which is interesting, and to infer something on higher dimension. Well, maybe we were a little too restrictive, so we were having a direct product. What about we relax our hypothesis of having one variable, I mean both variable fixed, like in separate variables, and we get one polynomial of one variable, but this second one has two variables. So I'm going to work in, how to say it, I'm not going to even write it down, but it's like C1.5. Okay? It's in dimension 2, really, but I still have one variable which is one-dimensional where I know things when my life is easy. Okay? So, well, the idea is to use skew products to get new behaviors and answers. Okay? And a skew product is simply a map which is two-dimensional in the first variable and one-dimensional in the second variable. All right? So now, remember what my hypothesis was. My hypothesis was that these two maps, so this is a polynomial again, as in our setting. And the goal is, if I find a wandering domain, a wandering Fatou component for this map in C2, since it extends to P2 of C, to the complex projective space, I will be able to have a wandering domain also over there, if my wandering domain is well behaved enough. Okay? All right. So in this setting, since I have that G of 0 is 0, what happens to f of z0? So W equals 0 is a fiber. Okay, now it's a whole complex plane. What happens to this map? Well, let's do the math. So this is, simply f of z0, G of 0. Okay, but now you tell me, okay, what are you doing? G of 0 is 0. So in here, I have 0, which means that the fiber W equals 0, which is a complex plane, I'm writing it like this for simplicity because it's fastest, but this is the set of ZW in C2 such that W is 0. Okay, this is an invariant fiber. Under F, right? if you remember my picture in here, so I'm taking here W equals 0. And now if I expand it, well, this is again, I mean, this was a complex plane. You see, this is a complex plane. It's a CW in C2 having W equals 0. So this is a C in C, Z0 with Z in C. So I have a complex plane. And what happens? Well, what's the map acting on this invariant fiber? Is this map. I mean, this map, I can consider F restricted to W, little f restricted to W equals 0. And that map is again a polynomial, and it's one-dimensional. So it's invariant under F, and the action of F restricted to W equals 0 is given by little f0 of Z, which is, by definition, little f of Z0, which is again one-dimensional, a one-dimensional polynomial. So I have it here, little f naught, and I will today I will stick to the schedule, and even if we had this 2 minutes break, I will finish 5 minutes before 10:30. So at 10:25 I will finish. I promise this to Raphael. So, and since I was spoiled and they also cleaned my whiteboard for me, I owe them. So now I have this one-dimensional map, which is again a polynomial of a given degree. Well, okay. So which kind of Fatou components can I have? Only pre-periodic ones, and so up to and iterates, only invariant ones, who are going to be nothing more than attracting domain, parabolic basins, or Siegel disks. This is what I can get. So I have my one-dimensional Fatou components in here, but these are one-dimensional. These are not telling me what happens to the two-dimensional pictures. So now we have natural questions. So the natural question so in here, well, if, okay, let's say it like that. If omega is a Fatou component, so this is not a question. The questions arrive afterward. If a Fatou component for capital F, then the projection of the W coordinate of omega, well, look at the iteration. In here where we iterate, this is a mess because it's going towards being non-autonomous. At every step, I will have to put back f of ZW and g of W inside. So this is a mess. This is something that you don't want to compute. But this is easy. This is simply g iterated k times. Okay? And so if this family was normal, this one has to be normal. So the projection of omega on the W coordinate is going to be, well, let's call it omega g naught, a Fatou component, one-dimensional. Let me write it one-dimensional, because otherwise we're going to lose ourselves in the air. A one-dimensional Fatou component is a one-dimensional Fatou component for little g naught. And so, yes?
Did we choose W is equal to 0 since it's an attractive point?
Sorry? Since it's?
An attractive super.
No, for the moment we don't know anything. I chose W equals 0 just for the sake of simplicity, because I can. I mean, if I have a fixed point somewhere, I can put it, I can translate and put it back wherever I want, and this is a conjugacy. And so, well, I put it at 0 just because it's easier when you write down things. But what I'm doing here is essentially this. So if I have a Fatou component for capital S, then I get a Fatou component for little g. And so now I'm going to put this Fatou component at 0. Like there is a fixed point somewhere. And my fixed point will be 0. And I will simply consider what happens to 0 as a fixed point. Is it attracting? Is it repelling? Sorry, it's not going to be repelling because I'm in a Fatou component. So is it parabolic or is it elliptic? That's the only thing that I'm going to do. okay? But the choice of 0 is not important. I mean, it could have been infinity. I would have changed coordinates and put it back to with 1 over w to 0. So, I mean, the first thing that I did, I put myself in this C2 case so that my fixed points are all at finite, in the finite part. And now, if in here you had 10,000s, you simply conjugate by w goes to w's minus 10,000, and you put it back at 0. That's a armless conjugacy, okay? And so, well, since this is a one-dimensional Fatou component for G naught, it has to, well, up to iteration, yes, up to an iterate, we can assume that omega G naught is G naught invariant. And so we have either, so it's either an attracting basing or a parabolic basing or a Siegel disk. So now I have my invariant fiber in here, and I have, so I'm going to put it in red. I'm finishing, I'm promising. I still have 2 minutes. So I have this is my omega naught, okay? It might be that omega naught actually is only on this side. For the moment, let's take an attracting basin, just to have an idea, okay? Because I still have to go to the questions. And here I have this one-dimensional Fatou component for F naught. But as we saw, you can do the exercise. If you try to iterate this guy, this is going to be a mess. This is not going to be autonomous. This is not going to be F composed with itself. This doesn't make sense. This is going to be a mess, okay? But you still can ask, is it true that locally there exists a bigger, well, two-dimensional Fatou component, which, when I intersect it with this invariant fiber, gives me this Fatou component? Well, that's the first question. So question 1 is, do one-dimensional Fatou components for F naught bulge to two-dimensional Fatou components for capital F? So bulging means that there exists omega capital F, a Fatou component for capital F, such that when I intersect it with w equals 0, gives me the Fatou component, yes, let's call it like this, omega F naught, a Fatou component for little f naught, okay? So if you want, if you project it on this invariant fiber. And question 2, imagine this happens, or imagine this doesn't happen, or imagine you don't know anything about it. Well, can we have a wandering Fatou component for capital F coming near my invariant fiber? I mean, can we have a Fatou component which wanders around and from time to time comes here and then maybe goes far away and then it comes back, go far away and comes back, but it can never smash itself on the invariant fiber, because if it touches the invariant fiber, it cannot be wandering again. It's going to continue to touch it, okay? So can we have this? And, well, I stole you 1 more minute, but I'm going to stop here for today. And so tomorrow, we will see what are the known results. So I will give you some list of known results on this. Then we will go forward trying to answer. So the answer to this, well, of course it depends on F, but it's yes. And this is why Sullivan's result is not true in higher dimension. And I will stop here for today. Thank you very much.